Hello. Uh, in this video, we're going to start on page 24. Okay, and I did the theory in part 1 of this video. Now I'm going to do part 2, which is basically answering the questions, right? So solving the problems. What is the source of the centripetal force required to make the moon go around the Earth? Now I proved to you in the first part that the force that the centripetal force is basically just gravity. So you can look at the first part, or even the part before the first part, part 0, I guess. It shows you how gravity is responsible for keeping the moon going around the Earth. Newton's assumed that the force that makes the apple fall is the same. We did that. So this force is the force of gravity, right, or the pull of the Earth. And I showed you how the 1.4 millimeter fall of the moon around the Earth. You can go back to the video and look at that. Now, astronauts experience weightlessness in orbit because the shuttle is free falling at all times. So when something is going around the Earth, it's technically free falling. It's just not falling on the Earth, it's falling around it. Okay. Now they have this spaceships now, where they're saying, like, if they can make them rotate, right, they will generate, if they can generate enough centripetal acceleration to match up with the acceleration of gravity, then the people will feel like they are at home. There will be no weightlessness issue. Now the only thing is, like, they have to make the radius of these things extremely large so that when you walk in on the inside of it, it almost feels like you're walking on a flat surface. Okay. And also, so we can end up with an acceleration of gravity of 9.8 or 10. So the centripetal acceleration is v squared over r. You want this acceleration to be about 10 or 9.8. V squared over 1700. And if you do the math, you should get about 130 meters per second, which translates to about 300 miles per hour. So if this spaceship is spinning at 300 miles per hour, right, then we can simulate the gravity. So we can have artificial gravity equal to our gravity on Earth. This is all stuff I talked about. All right, let's take a look at some examples here, and then we move on. So the standard is, if you have one mass m here, one mass m here, separated by one distance d, we say the force is 1F. Okay, so I'm just going to pick some here. So let's look at the last one here. If the mass is staying the same, this mass is tripled. So Fg is proportional to the product of the masses over the distance between their centers squared. So this mass hasn't changed. This one is 3 times as much, and the distance hasn't changed. So the force here will be 3 times what it is up here. Let's look at this one here. The masses haven't changed, so that's 1 times 1 over. Now, the distance between their centers is cut in half, so just 1/2 squared. And this is just 4 times the force. And you can do this conceptually, technically, really. If the distance is cut in half, the force has to increase, but it doesn't increase by twice as much, it increases by 4 times as much. That's because of the inverse square law. So let's look at, I don't know, we can look at this bottom one here. So the mass is 1/3 as much, this mass is 1/4 as much, and the distance between them is 5 times as much. So now if you do the math, you get 1 over 12 times 25, and you can do the math for that. That looks like 300. Okay, if we do the very last one, and we want the answers to be as fractions because it's easier to compare. The mass here is 1/3 as much, and this one is 3/2 as much, and they're separated by distance of 8. So you have to square the 8. All right, so this should be 1 over 128 times the force that we had up here. And you should realize here that the distance has a bigger influence than the masses, right? Because the distance is squared. Okay. Now this is the formula we're going to be using to do calculations. So this statement here is just to compare. Now if you want to find actual values, this is what we're going to use. Now the units for G are easy to come up with. So whenever you want to find the units of any quantity, all you have to do is isolate it. So if I isolate the g, it's going to be Fg r squared over m1, m2. Okay. So if I do the units here, it's going to be newtons meters squared over mass squared, which is kilograms squared. So that's why you end up with those units. Now, this number here is extremely small. And that's what makes the gravitational force a weak force. Now, it doesn't have any significance until the masses become extremely, extremely large. That's why we don't talk about it between like small objects, objects we deal with every day, like people, books, cars, and stuff like that. It's only important when you're dealing with planets or moons and stars and suns and stuff like that. All right. Calculate the force of attraction between the moon and the earth. Really, all you have to do is go to the data table and just do Fg. Use this formula. This is a given. The mass of the earth is given. The mass of the moon is given. And the distance between them, the moon and the earth, is also given on the side of that data chart. Okay. Now, if we look at B, we're going to do that in class. We did that in class. Suppose an apple at the top of a tree is pulled by earth with the force of 1 Newton, right? So this apple must be about 100 grams, 0.1 kilograms. If the tree were twice as tall, would the force of gravity in the apple be only 1/4 as strong? And at first you think that's what it is, because the tree doubled in the height, doubled in its height. But that's not true, because you have to measure the distances to the center of the earth. Okay, so whether the tree is twice as tall or 3 times as tall, the apple, right, hasn't changed much its distance compared to the center of the earth, right? So in order for this to be 1/4 as much, the tree, the height of the tree has to be equal to the radius of the earth. So if I put, this is earth here, and this is the tree, and this is exaggerated. If the apple is here, right? Well, that's the same thing as having the apple on the surface of the earth, because this distance here is too small compared to the radius. And even if I put the apple up here, right, at twice the height, let's say this is a height h, this is a height another h, this apple is still at the same distance towards the center, very close. I mean, a few feet more or less, it's not going to make a difference compared to 4,000 miles here, or 6.4 times 10 to the 6th meters. It doesn't make much of a difference. So the answer is no, because you are not twice the distance away from the center of the earth. Now, D is just common sense. When you are on earth, there's a bigger pull of gravity on you than when you are on the moon, right? So gravity is going to pull you harder than on earth than it does on the moon, so which means more energy is required to escape earth's gravity, if you'd like. Okay, so you're going to need more fuel. Now, part E. Jupiter is 300 times as massive as earth, but an object on its surface would weigh only 2.5 times as much as you would on earth. What is the ratio of the radius of Jupiter to earth? Okay, so this means that Jupiter must be much, 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 much bigger in volume than earth. So because the object has to be extremely far away from its center. Okay, so to only be 2.5 times the weight or the force of gravity. Okay, because it's pretty massive, but it's also a bigger object. So let's see how we can do this. Now, F on earth is big G, the mass of this object, whatever object it is, mass of earth over the radius of the earth squared, because you're right at the surface of the earth. Now, F on Jupiter is equal to big G, the mass of the object, the mass of Jupiter, over the radius of Jupiter squared. Okay. So we have to figure out what's common here. So now Jupiter is 300 times as massive as Earth. So I think I can replace this mj with 300, the mass of the Earth. Okay, and I can see there is a bunch of things that are common here. So we just get a different color marker. I can see that these things here are here also, right? So if I isolate this expression here, I can plug it into here. So let's see if we can do that. So I can see that it's going to be Fe, right, times Re squared. In other words, I multiply these two together to get whatever is circled here, which is the same as up there, times 300, because that's still there, over Rj squared. Now it's telling us that the weight, or the force of gravity, is 2.5 times as much as it would be on Earth. So instead of Fj, I'm going to make this 2.5 Fe. All right, so let's see what we can accomplish here. I think I can divide both sides by Fe. So now this is what I'm looking at. I'm looking at 2.5 Rj squared equals Re squared times 300, or 300 Re squared. Right? Since we're comparing the radius of Jupiter to that of Earth, I'm going to divide both sides by Re squared and 2.5. So this should be 300 over 2.5. Now this has to be squared. I put the square on the outside. Now if you want to find Rj over Re, you take the square root of 300 over 2.5. Now let's look at some conceptual questions here where we have to explain. Two asteroids with masses of m and 3m exert gravitational forces on each other. A student contends that the force will be in different direction and of a different magnitude as shown. All right, there's a lot of things wrong with this. First of all, these two arrows have to be the same length, right? And that's because of Newton's third law. So if A exerts a force on B, B has to exert the same exact force on A. And the other thing is that the force of gravity, or the force of gravity, or the gravitational force, is an attractive force. It doesn't repel, right? So it's always attracting. So the arrow should be facing inward, and it should be equal in size. All right. For this one here, I read it earlier, so the answer to this is none of the above, okay? Okay, because we can tell the mass of A in terms of m. Because look, if we think of the force between B and C as F, and these two are separated by distance d, right? Now, if the distance is quadrupled, the force, and let's just assume that this has a mass m, the force will be just 1/4 as much, because now you double the distance, you have to follow the inverse square law. Now, in order to end up with an F here, because this is not, there is no net force. I'm not saying it's not moving. There is no net force. So in order to end up with F here, I think this has to be 4 times as much, right? Because it's directly proportional to the product of the masses. Okay. We're looking at RT17. Okay. 3 objects, each with a mass m, exert gravitational forces on each other. Which of the arrows below show the direction of the net force on mass B? Well, the forces are going to generate from B. Okay, so we're only concerning ourselves with B. So B is attracted by A, and it's also attracted by C. Okay? And they all have the same mass. So the force between B and A is the same as the force between B and C. Okay? So now if we do head to tail, we can take this guy, put him here, right? And the force will be in that direction, and this angle here should be 45 degrees. So the answer should be I. Just going to see what's on the agenda. Okay. All right. These problems here are just literally just following the math. So I'm not going to do it all the way, but I'm just going to show you what you have to do. Now we can write r squared here, or we can write d squared. I'll write r squared. And r is basically the distance center to center. Now in the case of people, it doesn't make sense. It doesn't make a big difference whether we go center to center, surface to surface. Kevin has a mass of 70 kilograms. Jenny has that mass. They're standing on the dance floor. They're 20 meters apart. Find the gravitational force between them. Now, if you do the math here, you should find it to be extremely small. And the problem is that it's because of that 10 to the negative 11 for the G, for the constant of universal gravitation. So here you just put the constant, which is 6.67 times 10 to the negative 11 newtons meters square per kilogram square. Okay, you put that in there without the units, of course. Put the masses of Kevin, Jenny, and divide by 20 square, and that's it. Two balls have their centers of mass 2 meters apart. One ball has a mass of 8 kilograms, the other is 6. What is the gravitational force between them? So that's another easy one. So you just have to plug in. So you plug in G, plug in 8, you plug in 6, and you divide by 2 square. If the mass of one of the balls is doubled, how will the force compare? Well, if one of the masses doubles, I think the force just has to be twice as much as before, because we haven't changed the distance, right? We haven't changed the other mass. We only changed one of the masses. All right, the one with the electrons. Two electrons are 1 meter apart. If the gravitational force between them is that weak, say how small it is, what is the mass of each electron? Now, Fg is going to be based on this formula. Is 6.67 times 10 to the negative 11. Now, an electron is an electron. It doesn't matter what kind of electron it is, what the element it belongs to. So an electron is an electron. It has the same, all electrons have the same mass. They are all identical. So now here it's m times m, which is m squared. A lot of people make this 2m divided by 1 square. And the force is given, which is right there. And you can find, if you can find the mass. If the distance between the electrons is doubled, well, if I double the distance, I have to follow the inverse square law. So my force will drop, but it will not be cut in half. The force will be cut by 4. Okay, so 44. A mass weighs 9.8 newtons on Earth's surface, right? So which is about 1 kilogram. How much does this mass weigh 100,000 meters above the surface? So we have to get ourselves to the center, right? Okay, so I can do this. I can just find the Fg by doing big G. The mass of this object, which is really about, I guess it's 1 kilogram. If we use 9.8, if you use 10, it will be a little different. It will be 9.8 divided by 10, so I guess we can make that 0.98 if you like. Times the mass of the Earth, right, which is 6 times 10 to the 24th power over. Now, how far is this object from the center? Well, it's the radius of the Earth plus that altitude, right? So which is 1 times 10 to the 5th power, and you have to square that. That's one way of doing it. Another way of doing it, which I think is quicker, is, okay, well, F at the surface, Fg at the surface, is big G, the mass of this object, the mass of the Earth, over the radius of the Earth square. Okay, now, the force at this altitude or height, I guess, is just going to be big G m of Earth over. Now the distance now is just, it's going to be r e plus that height square. Okay. Now we can see that these two quantities that I'm going to circle are exactly the same, which means this product here has to equal this product. Okay? All right, so I'm going to say, well, F, and this is actually, I mean, probably the first way I did it is easier, but this is just in case you are not given a number here. You're giving no numbers. Just giving like a mass weighs whatever, a W. So Fs times Re square equals F at this height times Re plus 1 times 10 to the 5th square. Now the F at the surface is 9.8. Okay, and I think you can figure out the rest. You can find FH here. Now the answer key on Haiku, the written answer key, does it completely differently. I'm just relying on the inverse square law. So if you can follow the way I do it on the answer key, go for it. If not, you can do this process here, which makes it a little bit easier. All right. And just pay attention to the words above and altitude and things of that nature. If an object's mass is 50 kilograms on the surface of the Earth, how much will its mass be 400 kilometers above the Earth's surface? Well, I really don't care because it's asking me about the mass of it. So the mass is not going to change. So don't confuse mass and weight. Okay, if the mass of the Earth were to double, what would happen to the weight of an object that now weighs 200 newtons? Well, Fg is proportional to the product of the two masses over the distance between their centers squared. Well, the object is not going to change mass, but the Earth will be twice as much, and the distance is to the distance between the surface of the Earth to the center of the Earth. So if one of the masses doubles, I guess the weight will just be 400. Okay, we're on number 47. What would happen to your mass if you were on a spaceship 25,600 kilometers from the center of the Earth? You got to pay attention here. It doesn't say weight, it says mass. So the mass does not change no matter where you go. By what factor would your weight change if you were 25,600 kilometers from the center of the Earth? Now, I'm going to do the quick, actually, let me do the long way. So W equals, or Fg basically, that's the weight, is big G, your mass, the mass of the Earth, over the radius of the Earth squared. This is at the surface of the Earth. Now, at this other location, at this height, we're going to call it W2, I guess. It's big G, M, your mass, mass of the Earth, over. Now, that's already saying from the center. So that's 2, 5, 6. So it's going to be another 3 zeros. Okay? So I can say that it's 25.6 times 10 to the 6th. Right? And I did that on purpose because I want it to be written as, I want the exponent to be 10 to the 6th power. So I can compare it to the radius of the Earth, which is also 10 to the 6th. Now, you see that these two parts are equal to each other. So, which means this product is equal to this product. So, W times Re squared is equal to the new weight times 25.6 times 10 to the 6th power, right? And there is a square here, square. And the radius of the Earth is 6.4 times 10 to the 6th. Now you probably noticed, or you can do the division, this is 4 times the radius of the Earth, but you don't have to see that. So I can say that W2 is equal to W times, this is a square here, 6.4 times 10 to the 6th over 25.6 times 10 to the 6th, and I'll square the whole thing, right? So this is a ratio of 1 to 4, so your weight will be 1 over 16 as much as what it is on Earth. Now here's the quicker way. If the weight is W, or Fg, on the surface of the Earth, when I go to this new place, it's going to be smaller, right? But smaller by how much? Well, it's by the ratio of the radius of the Earth to this new radius squared, because it follows the inverse square law. So it's the ratio of the radius of the Earth to this 25.6 times 10 to the 6th power. So it's going to be 1 over 16 as much. All right. An object that weighs 25 newtons on Earth. Now, you probably can say, well, I'm just going to get the mass, right, and just work with the other planet. But it takes too long. I think if we can just do proportions and follow the inverse square law, we'll get there quicker. And the fact that the force is directly proportional to the product of the masses, we can probably get there quicker. An object that weighs 25 newtons on Earth is placed on another planet. Okay, so on Earth is 25, big G. The mass of the object, the mass of the Earth, over the radius of the Earth square. And the reason I'm doing it this way, because I might tell you, I might not give you a number here. I might say W on a, not even Earth, a different planet. Okay? Okay, let me go back to this. So I might give you just W, a different planet you don't know anything about. Now, this planet has the same size as Earth, but twice as massive. Now, I don't even need to do the inverse square law here because it's the same size, but the mass is twice as much. So the weight is directly proportional to the product of the masses. So the weight will just be 50. It becomes a problem when you're dealing with the distances. With the mass, it's pretty straightforward. Okay, we're looking at number 50. Okay, a planet's diameter is 2/3 that of Earth, which means the radius of this planet is also 2/3 the radius of Earth. The mass of the planet is the same as that of Earth. What can a 20 Newton object expect to weigh there on this planet? Now, I know that, let me see, maybe we can do this the quickest way possible. All right, so it's 20 newtons on Earth. Now the mass doesn't change, but the radius is 2/3 the radius of the Earth. So if you just think about that conceptually, whatever you're going to end up with at the end has to be greater than 20. And the ratio you want to put in here, you're going to put 3 to 2. And you square that. Because if you put 2 to 3, you're going to end up with something that's less than 20, which is not true. You want to end up with something that's bigger than 20 because you shrunk your distance. You're getting closer to the core, in other words. Now, for those of you who don't see this, you can do this. Well, it's 20 on Earth, which is big G, the mass of the object, the mass of Earth, over the radius of the Earth square. Well, you're going to say, what is it? Okay. At this other, on top of this other planet. Well, this is the mass of the planet. Now, it has the same mass as Earth, so I'm just going to write ME here. But the radius of this planet, it's 2/3 the radius of Earth, and I have to square the whole thing. Now, I can see that whatever I circle here is the same in both equations. So if I make this product here, so if I do 20 times RE square equals W times 4/9 RE square, right? So it's going to be, W is going to be 9/4 of 20, okay? No, but I think the previous way is much quicker, if you could do it that way. Right. You avoid writing two equations and manipulating the equations. Number 51, a planet's mass is 4 times that of Earth, and its diameter is twice the diameter of Earth. What will a 22 Newton object weigh on that planet? I think this is pretty straightforward. The fact that the mass is 4 times as much will make the weight or the pull of gravity 4 times as much. But we also double the diameter, which means we double the radius. Now, which means that the force is going to be cut by 2 squared. Okay? So you multiply by 4, you divide by 2 squared, you end up with 22 newtons at the end. Okay. A planet's mass is 10 times that of Earth. Okay? And 5 times the diameter. So let's see if we can do this the quick way. And I'm going to see what happens by just making changes in steps. So the fact that the mass is 10 times as much, this 20 Newton object will weigh 20 times 10, because the mass is it's a direct relationship. And it's 5 times the radius. 5 times the diameter is the same thing as 5 times the radius. Now, which means now we're further away from the core, so the force is going to be smaller by 5 square, right? So I cannot, if I multiply by 5 square, that's not a good idea, because now you're just making the force bigger. I know that the force is going to shrink by 5 square. I hope you guys can see that. Okay. Some of them are easier than others. Let's look at 27. A 27 Newton object on Earth weighs 32 on a different planet. So this is what I'm going to do. I'm going to say 27 equals g, the mass of this object. Now you probably can find that the mass of this is 2.3, and you can go back to the data table and find the mass of this planet. You just take 1/3 times 6 times 10 to the 24th. It's a lot of work. And you are expected to answer a question like this in about a minute. Okay? So big G, the mass of the object, the mass of the Earth over the radius of the Earth square. Now on the other planet, it's going to be 32 equals big G, the mass of the object. Now the other planet has a mass that's 1/3 the mass of Earth. Okay? And this is the radius of the planet square. Right? So I noticed that if I take this 3 and I move it here, whatever I'm circling is the same. So now I have 27 RE square equals 32 times 3 RP square. Now I want to compare the radius of this planet, or the diameter, to the radius of Earth. So I'm going to move this RE square down here, and I'll square the whole thing. And I'll take this 32 times 3 here. I can make that a 1, I make this a 9, and at the end you have to take a square root. So you should know how to do the algebra there. Okay. This one talks about, this RT18 talks about the net force on each object, and we need to compare them. Now, the way I deal with this is I say, you know what? I'm going to set a standard. So when I have one mass interacting with another mass and the distance between them is 1d, the resulting force is 1F. And I'm going to base everything on that. Now let's concentrate on A. Well, A feels a force from B. Well, M has twice the mass, same distance. This one didn't change, it's 1M. So I think this force, based on this standard, is 2F. Now let's look at the force that A feels because of the presence of C. Well, the force is going to be twice as much because the mass is doubled here, but also the distance is doubled. So I'm going to double the mass, and divide by 2 square, because the distance is double. So it's 2 divided by 2 square. So it's going to be 1/2 the force. Well, if B exerts a force of 2F on A will exert a force of 2F on B. And if C exerts 1/2 F on A will exert 1/2 F on C. Now we just have to look at the interaction between B and C. Well, B exerts feels a force of 1F because the masses are M and the distance is D, so this is 1F. Okay. This mass here, okay, feels also a force of 1F. Newton's third law. Whatever force B exerts on C is equal to whatever force is C exerting on B in the opposite direction. And now to find the net, if they are going in the same direction, you add. If they're going in opposite direction, you subtract. Okay. Now, for the theory for the acceleration of gravity, you can look at the previous video, the very first video, and I was showing you. I proved that a formula for G, which is big G, the mass of whatever is at the core, whatever is providing this gravity, over how far you are from its center. So this R is not the radius of the planet, but it's how far you are from its center. Okay. So an astronaut goes out for a spacewalk at distance above the Earth equal to the radius of the Earth. So now this person is 2 times the radius of the Earth away from the center of the Earth. So the acceleration of gravity will follow the inverse square law. You can see it here in this formula. So the acceleration of gravity will just be G over 4. This one here, I'm going to treat it as if it's not Earth. I'm going to try this as if I'm dealing with a completely different planet, so that if you're not giving numbers, you should be able to handle this one. So G is on the surface of the Earth. Big G, mass of Earth, over radius of the Earth square. Okay? Now, when you are a certain height above the surface, you get 0.54 G. And that's big G, a mass of Earth, over R squared. And R is not the height, but it's how far you are from this location we're talking about to the center. So the way we're going to handle this, we're going to find R, and if you want to find the height above the surface, we're just going to subtract the radius of the Earth, because this distance here takes you all the way to the center. All right. So I can see that these two are equal. So I can say that 0.54. And by the way you do the algebra, that's up to you. You can do the division. You can take this whole thing and substitute it in here. You do whatever you want to do. Just keep it simple, that's all. Now I can get rid of the no, this is just not 0.54, this is G. I can get rid of the G's. I can find R, and then once I find it, make sure you subtract the radius of the Earth to get the height. If it says how far from the center, then we don't have to do anything. And that's why in the video I say that this m here is the mass at the center. The Earth has a mass of that much, a radius of that much. Find the acceleration of gravity that high above the surface. So if you want to find G, you're going to do big G, which is given, the mass of the Earth, which is up there, over how far you are from the center of the Earth. So that's going to be 6.4 times 10 to the 6th plus 1 times 10 to the 7th power. So basically, if you want to make this, you can put everything in the calculator actually, and you would square, because this one says above the surface, okay? Or you can make this 10 times 10 to the 6th, whatever you want to do. Now it's all calculator. The instrument carrying the payload for a rocket weighs 1,058 newtons on Earth's surface. What does it weigh when that distance above the surface of the Earth? Now I'm going to do the quick shortcut, right? Following the inverse square law. The mass doesn't change. We're dealing with Earth. So this 1058 is going to go under some changes. Now it's definitely going to be less. Okay? Less by how much? Well, by the ratio of the two distances, and you're going to square that. Okay. Now, when you are at the surface of the Earth, that's going to be the radius of the Earth. Okay. Now you can do this with two equations and come up with it. And if you can't see it, you just come see me and then we'll talk about it. Okay. I want you to kind of like learn it this way. It's quicker. And then this is going to be 6.4 times 10 to the 6th plus. Now I can see that I can write that as 25.6 times 10 to the 6th power, right? Breaking the rules of scientific notation. And the reason for that is because this 25.6 is 4 times 6.4. You should be able to notice that. If you don't, no big deal. Just do the division square. So this 1058 will be, this is 1 to 5, so it will be 1/25th as much. So 1058 divided by 1/25th. Okay. Now the answers that I have on the answer key on haiku, I did them a completely different way. So this is just a different approach. If you understand it on the answer key, go for it. It's all algebra. So how you do the algebra, I'll leave that up to you. Now find the moon's acceleration around the Earth. So now we're trying to figure out how much acceleration the moon feels because of Earth's presence. Now, by the way, you don't have to have anything upward at the location of the moon to talk about the acceleration of gravity. Okay? because the acceleration of gravity is just describing the gravitational field surrounding the Earth. So it's like if I say, is there gravity in this space here? You should say yes. I don't have to actually take a marker, put it there, and see it fall for you to say, well, yeah, there is acceleration of gravity, but there is gravity because I saw the marker fall. Okay, it's intuitive, right? You should know that there is gravity in there. Find the most acceleration around the Earth. So now we're just going to use this formula. Going to put in the constant g. This is the mass of the Earth because that's what's at the center. And this r is the distance between the Earth and the moon, center to center. And I did this in the proof to show you that the centripetal acceleration of the moon is nothing other than the acceleration of gravity. So that should be 0.0028 or 27. Okay, this one is a little tricky. It takes an object t seconds to reach the ground on Earth when dropped from a height h. How long in terms of t will it take to hit the ground from the same height on a planet where the acceleration of gravity is 1/3? Now keep in mind that the time has a square, right? So it's not direct. So this is what I would do here. I would say, you know what, this is the height on planet Earth. Okay? This g is g on Earth. Now we're going to drop it from the same height on a different planet. But on this planet here, the g is 1/3 of the g on Earth. And we're trying to find the t on this planet, okay, in terms of t. Now, I can maybe set this equal to each other. And if you do, you should see that t squared is going to be equal to 1/3 tp squared. This is the t, the time that it's going to take to fall on that planet at a height h. So tp is equal to radical 3 times t. And you should know that it's going to take a longer time because there is less of a pull of gravity. So if this is a multiple choice, you do not look for anything less than t. You have to look for something that's bigger than t. This number is bigger than 1. Okay. A dropped object falls 5 meters in the first second. Okay, this is on Earth. How far down will it fall in the first second on the moon where the acceleration of gravity is 1/6? Well, if I write h equals 1/2 g t squared, they're talking about 1 second, so the time is fixed. But if you look at the relationship between h and g, that's a pretty direct relationship. So if I cut the acceleration of gravity by 1/6, the height will be cut by 1/6. So instead of 5 meters, it will be 5 times 1/6. For those who can't see it that way. Okay. This is the new height on the, so this is a 5 basically, right? And this is a 1. This new height is 1/2. Well, it's 1/6 of g, and we're talking about 1 second. Okay, so if I move this 6 here, I can see that the right sides are equal. So I get h equals 5/6. Okay. Jupiter is the largest planet in our solar system, having a mass of radius and radius that are respectively 318 times. Okay, so 318 and 11.2. So the mass of Jupiter is 318 times the mass of the Earth. The radius of Jupiter is 11.2 times the radius of the Earth. Suppose that an object falls from rest from the same height near the surface of each planet before striking the ground. Compare the time of fall on Jupiter to that of Earth. So I think what we need to do here is probably compare the g's first, because we're going to need that. And the reason is h equals 1/2 gt squared, right? So maybe I should find the g's, and since it's the same height, I can set them equal, and then we can take it from there. Okay, so g on Earth is basically big G, the mass of Earth, over the radius of Earth squared. Right? There's a quicker way. You can do it quicker just by looking at those numbers, and I'll show you in a second. But this is the long way. G on Jupiter is big G, the mass of Jupiter, which is 318 times the mass of Earth, over, now the radius of Jupiter is 11.2 times the radius of Earth, and I have to square. Okay. Now, I'm going to go to the height. So they're falling from the same height, right? So this 1/2 gt squared will be the same for Earth and for Jupiter. So we just have to compare the times. So I'm going to say 1/2 g on Earth times t on Earth square, I guess, equals 1/2 g on Jupiter times t on Jupiter square. All right? Because those two expressions represent height, and which is the same on both planets. So I can probably just multiply both sides by 2. I'm going to leave this as GE. I'm going to leave this as TE square equals. Now I'm going to replace this GJ with this number here. Okay, so maybe I should replace the GE with big G, mass of the Earth, over RE square. This is the slowest way of doing it. Times T on Earth square equals big G times 318, the mass of the Earth, over 11.2 radius of the Earth square. So I'm going to square both of these separately so I can start reducing stuff here. And then I have T on Jupiter square. So a lot of things are going to go. All right? So which means T on Jupiter, okay, is equal to 11.2 square over 138, right? This is square, T on Earth square. Oh, 318. This is 318, sorry. 318. So 318 down here. Okay, so T Jupiter equals 11.2 over radical 318 times T on Earth, right? And I don't know if I have the answer to that. So it should be about 0.63. Yeah. Okay. Now, if I want to do the accelerations quickly, okay, I'm going to try to do it without going through what I'm erasing now. Okay. Now, G on Jupiter is equal to G on Earth with some changes. Now, the mass of Jupiter is 300 times as much as the mass of Earth. So the G will increase, if it was just for the mass, it would increase by 318. But the radius is also bigger. So the G will decrease by 11.2 square. Okay? Then you just come here and you say, well, this is GE TE square equals GE 318 11.2 square times TJ square, and you can figure that out, right? This is quicker if you can do it this way. If not, you can always go back to the long way and do it the long way. The only concern is that you're spending too much time on if you start to plug in numbers and solve a bunch of equations. Okay, what is the distance from the Earth's center to a point outside of the Earth where the acceleration of gravity is 1/10 of its value at the Earth's surface? So I'm going to do it the long way first, because you're probably looking at it and it's like, I hope he does it the long way. So I will. So this is big G, the mass of Earth, over the radius of Earth square. Okay, good. Okay, so we're looking at from the center, so we don't have to worry about the height or anything like that. Now, G at this other location is 1/10 of what it is on Earth. And that's big G, the mass of Earth, over this radius square. Okay, now we have to find out what this R is. So a lot of ways I can do this. I can take this and put it in here. Okay, so we end up with 1/10 big G, mass of Earth, over the radius of the Earth square, equals big G, m of Earth over R square. So if I cross out this stuff here, I get R equals radical 10 times the radius of the Earth, right? Again, the way I did it in the answer key is different than the way I'm doing it now. Another way we could do it is that we can say, well, the ratio of the gravities is going to be 1/10. Actually, probably it's easier to just do it the other way. Okay, so I don't want to confuse you with this. Okay. At a given point above Earth's surface, the acceleration due to gravity is 7.82 meters per second squared. What is the altitude? So we're looking at above the surface. Okay? Okay. So I'm going to say G at the surface is, which is really, I guess we're going to use 10 equals big G, mass of Earth over the radius of Earth square. Okay. Now at this other location, it's going to be 7.8 equals big G, mass of Earth over the radius square. Now that's height plus the radius. So when you're done, you have to subtract the radius of the Earth. Okay. Now, how do we solve this? Well, I can just say that 10 RE squared, if you don't like to divide, this product is equal to this product because this, what I'm circling now, is equal. Okay? And you can just figure out what R is. Okay. Now, another way of doing that, you can say, you know what? Well, the acceleration of gravity became 7.8 from 10. How did that happen? Well, I must have done the radius of the Earth over this new radius square, right? And you can divide here, take a root, right? And I guess you can flip this. So 10 over 7.8. You can flip this. You got the idea, right? Multiply by the radius of the Earth here. Going too fast, but you should be able to follow, or pause and go back and see how I did it. The algebra, that's something you have to deal with. Okay. All right. In both cases shown at right, an asteroid is a distance x from a moon. The two cases are identical except that in case A, there is a large planet directly between the asteroid and the moon. Is the gravitational force on the asteroid by the moon greater in case A, greater in case B, the same in both cases? It's the same. Because whether there is another object in between or not, we're looking at the force between the moon and this person. Okay, that force is only going to depend on the distance between them and their masses. So it's not gonna matter whether there is something in between or not. Now here, this is something I proved to you in one of the videos, so I'm not going to do it again, so you can watch the video. The velocity going around, an object that's going around a planet or a sun, its velocity is big G. This is the mass, not of the object, but the mass of what's at the center, whatever you're going around. And the reason for that, because all objects, as long as they are the same height, or they're falling at the same rate, they're going to have the same speed, right? Because they are all falling and all objects fall at the same rate. So the mass doesn't matter. So if I have a satellite that's 10,000 kilograms and a satellite that's 5,000 kilograms, and they are at the same orbit, in the same orbit, they're going to have the same speed. And here we lose that r squared. And you can go back to the proof in the previous videos. Now this is the mass of what you're going around. This is how far is this satellite or the moon from the Earth, whatever. Okay? So here's a question here. Satellite A has twice the mass, so at the end of the day, they should have the same speed. Okay? Because they are both falling. That's your explanation conceptually. If you ever have to explain it conceptually. Okay. So V equals square root of GM over R, the whole thing under a radical. All right. Now here you have to pay attention to the word altitude, right? The Earth has a mass of that. What's the acceleration of gravity at this height? So I think we can just say that a G is equal to a big G, mass of Earth. I could have done proportions, but sometimes it's just we can just put the numbers in, okay, divided by r squared. Now r will be 0.6 times 10 to the 6 plus the radius of the Earth, okay? And if you do the math, you should get 8.17 meters per second squared. What's the tangential speed? Okay, what tangential speed must the satellite have to maintain this orbit? Because it's always going tangent, the satellite or the satellite is always going tangent to the orbit, right? It's perpendicular to the radius. So to find the speed, we can just use this formula here. So we can just put in g, which is 6.67 10 to the negative 11, the mass of the Earth, and we put the radius, which is 7 times 10 to the 6th. That's it, the height plus the radius of the Earth. These are easy, they're just math. Okay. Now, a spacecraft has a mass of 3,000 kilograms. Okay. How long does it take to make one revolution in hours? Okay. So, we have to find, I'm sorry, it says to find the speed first. So to find the speed, you just do g, the mass of the Earth, the mass of the spacecraft has nothing to do with it. It's falling, whether it's 3,000 or 20 or 30,000 kilograms, it doesn't matter. And this is 200 kilometers above the surface. So a couple things we have to do here. We have to change kilometers to meters, and we have to be aware that's above the surface. So it's going to be 200,000 meters plus the radius of the Earth. That's what the r is. Now, if you do the math here, you should get 7786.94 meters per second. Right. How long does it take to make one revolution, to go around once? Well, we're just going to go back to velocity is 2 pi times the radius of the orbit, which is the circumference, basically. The whole top is the circumference over period. We have the speed. We have this radius, which is 200,000 meters plus the radius of the Earth, and I think we can figure out the rest. And the period is 1.48 hours, right? And a low orbiting satellite takes about 90 minutes to go around the Earth, and that's a pretty low orbiting satellite. That's just about, if I have to guess, that's probably about 120, 130 miles above the surface, which is not that much. What's the net centripetal force? Now, all these three questions here are exactly the same. So the net centripetal force is the gravitational force, attraction between the objects. That's also the weight. Okay, and I think we proved that a while back in one of the videos. It's all the same. So I can just find one of them and move on here. So let's say which one is the easiest. I probably did the net centripetal force. That's m v squared over the radius of the orbit. Now the v we found earlier, the mass. Now this mass here is the mass of the object. It's the mass of what's going around, not what you're going around. Okay, so that's the spacecraft divided by this distance, which is 200,000 meters plus the radius of the Earth, right? And you do not square that, if you remember the centripetal force stuff. What's the force of gravitational attraction? It's the same thing. The weight is the same thing. Now, I could have started with the force of gravitational attraction and just say that these two are the same. I could have done Fg, big G, the mass of the spacecraft, the mass of Earth, over the separation distance between them, which is basically 200,000 meters plus the radius of the Earth, and you would square that. Sorry about the coughing. It's not feeling good. All right. Okay. What is the height h? And some of this we're going to do with the probably could. Let me see. All right. I'm going to come back to 6. I'm going to label some of this. I'm going to come back to 63, and I think 64 when I do the third law. Yeah. I'm going to come back and do it this way. And maybe even 65. Okay, so maybe we can try this. If I don't get to them now, we'll just do them in class. 64. What is the height h above the Earth's surface at which all geosynchronous satellites must be placed in orbit? Now, geosynchronous means like they're synchronized with Earth. So they have the same period of revolution as the Earth's rotation. So in other words, their period is 24 hours. Okay. What is the height h above the... Okay. So in order to do this, maybe we should do... so we don't know their speed. Actually, I think we should maybe find their speed. Yeah, I think this one is better if we do it with the third law. Yeah, this is a tricky one. It's going to take a while. So let's try it. 2 pi r over t is the speed, and that's also equal to gm over r, right? And this is actually what I used to prove the third law. It's going to be a pain. So this is 2 pi. This is what I'm going to do. I'm going to find the r, and I'm going to subtract the radius of the Earth later. It's probably quicker than... well, the way I did it in the answer key is the same thing. So r over... Now, 24 has to be changed to... 24 hours has to be changed to seconds. Equals a big G, which is 6.67 times 10 to the negative 11. Now, this is 6 times 10 to the 24th over r. Now, if I square both sides, this is gone. This becomes a 4 square and r square, and I have to square the bottom here, right? Now, if you this is going to be an r cube, so you take the cube root to get the answer. I hope you can see that. You can move this up to here. Okay, you can multiply both sides by this denominator, divide by 4 pi square. Just be careful when you divide by 4 pi square, you put that in parentheses. And if you take the cube root, you get the r. Okay. Now, we're definitely going to do 64 with the... what do you call it? With the third law. And maybe 65 too. The shuttle orbits about 200 kilometers above Earth's surface. Find its orbital speed and period in hours. All right, so I think we can find its speed first. So V equals big G, the mass of Earth, over... Now that's 200,000 meters in addition to the radius of the Earth. And there is no square, but there's a square root above this whole thing. So once we find the speed, we're going to say, well, this speed is equal to 2 pi r, which is this thing, over the period, right? Now, when you find in this period, that's going to be in seconds. So now, you already found the speed up here. You have this r, you can find the t. And that's going to be in seconds, so which means you divide it by 3600 to change it to hours. And I'm going to try to do that one also with the... maybe I'll try to do that one with the third law. 65 was not that, actually, 60, which was 65? Yeah, 65 wasn't that bad. But I think the one 64 was a little long. All right. A 500 kilogram satellite orbits 300 kilometers above the surface of Venus. Find the satellite's orbital period in hours. I'm going to put a mark on 66. We'll come back to it with the third law. So I'm going to say, you know what? Big G m over r as a square root equals 2 pi r over t. In other words, I just wrote the speed two different ways. This is the mass of Venus, which we can get from the data table. This is how far is this satellite from the center of Venus, so which means it's going to be 300,000 meters plus the radius of Venus, which I think is given to you. That's 6 times 10 to the 6th, okay? And this r here is given. And I think we can find the period in seconds and change it to hours. Let me see if we should do 66. Yeah, we said we're going to do 66 with the third law. A satellite orbits 600, again, above 600 kilometers above the surface of Mars. Find the orbital speed and orbital period. That's the same thing as before. Okay, this one is a little tricky. So it says find the speed of Venus in its orbit around the sun. So when you're doing this problem here, you put V here, that's going to be a constant. This is the mass of the sun, because Venus goes around the sun. And this r is the radius of the orbit of Venus. In other words, how far is the center of Venus from the center of the Earth, of the sun, sorry. All right, this is the third law. I'll do a quick reproof because I did the proof, I think, in one of the other videos. So I'm going to show you where this comes from. Now you can watch the video and fill in the blanks here. You're responsible for doing that. Now I'm just going to try to show you where this comes from. And that basically comes from the fact that the speed can be written two different ways. Now this r is the radius of the orbit. 2 pi r over t is big G m of whatever you're going around over r with the square root, right? So now, which means, okay, I'll write it. So which means if we square both sides, this becomes 4 pi square r square t square, okay? Now I'm going to put the r's and the t's to one side, keep them together. So it's going to be like r cubed over t square is equal to big G m over 4 pi square. Let me just double check on that. Here I have it written back upside down, meaning like t square over r cubed, which is really the same thing if you think about it. Now, so basically what this is saying, if this mass here is kept constant, meaning if you take two objects that are going around the same center, this becomes constant. This is constant. This is constant. Constant. What does that mean? It means something very powerful. It means that this ratio r cubed over t square is a constant. And I'm going to write that here. I'm going to keep it here so we can use it later. Now, unfortunately, this is not in your formula sheet. You can memorize it if you want to use it. So I don't ask you to memorize much. Okay? Okay. Which means what? It means that if I do the radius of the orbit for some object, a planet or whatever, cube over the period of that object square, that's equal to the radius of some other object b cubed period square. And I can keep doing this for all objects, but here is the trick, here's the catch. As long as they're going around the same center. You cannot use this for the moon and the earth. The moon goes around the earth goes around the sun. But I can definitely use it for our moon and one of our satellites, because they are both going around us. I can definitely use this for different planets in our solar system, because they all go around the sun. So it's extremely important you understand that. This mass has to be the same for both objects A and B. Well, I didn't finish that, but I think you can see how I go from here to here, right? You can just divide in this direction, right? Divide this bottom by this bottom equals this top by this top, right? Okay, so TA over TB, and you take the square to the outside, equals RA over RB cubed. Now, if the times are in hours, as long as they are both in hours, it doesn't matter, right? If the distances are both in miles, it doesn't matter because, again, it's all ratios, right? Okay. An asteroid revolves around the sun with a mean average orbital twice that of Earth. Now, the reason we say mean is because the orbit is not perfect. It's not a circle. It's an ellipse. And maybe in class I'll show you how you can draw an ellipse. Calculate the period of the asteroid in Earth years. So this is the asteroid. This is the Earth. So I'm going to compare it to the Earth. Square equals the radius of the asteroid, so insect here, over the radius of the Earth cubed. Okay. Now I know that the Earth has a period of 1 year, so I can make that a 1. And they're telling me that this ratio here is 2 to 1. So I can say that TA square equals 2 to 1 cubed, and you can solve that equation, which is not that hard to do. Okay. Calculate the time required for Mars to circle the sun in Earth days. Now, I know a lot of things about Earth. So whenever it says a planet that goes around the sun, my first instinct is to use the Earth as the other planet. So the time for Mars over the time for Earth square equals the radius of Mars, or the radius of the orbit of Mars, over the radius of the orbit of Earth, and that's going to be cubed. All right. So Earth takes 1 year to go around the sun. Okay. This ratio is 1.52. Cubed equals Tm square. So once you cube this, you take the square root. And we should get 2.83 years. It's a very long year on Mars because it's far away from the sun. It takes a longer time to go around. Okay. The moon has a period of that much and has a mean distance of that much from the center of the Earth. So we'll make sure we change that to meters. Find the period of a satellite that is in orbit that high, or that distance from the center. So this is what I'm going to do. I'm going to say, you know what? T, we're trying to find what? The period of the satellite. So I'm going to put satellite on top, just to make the algebra easy. Over T of the moon square equals the radius of the orbit of the satellite over the radius of the orbit of the moon cube. See how I'm not saying the radius of the moon? It's the radius of the orbit of the moon. Now the moon takes 27.3 days to go around. Now keep in mind that if you do it this way, you should get your time for the satellite in days, and you can change it to hours by dividing by 24. Now, the radius of the orbit of the satellite is, what is it? Is 6.7 times 10 to the third. So technically, I said earlier we have to change, but we don't have to because they're both in kilometers. So we can just leave that. So it's going to be TS over 27.3 square. And I highly recommend you don't square both sides in there, both part of the fraction. Leave it as is. Okay, it's much simpler. So this is the, for the satellite, this is 6.7, 10 to the third power over 3.9, 10 to the fifth power for the moon. You cube that first, take the square root, and then multiply by 27.3. Okay? And I'm sure you are pros at algebra. And you can do this, right? Now, another way we could have done this, and we'll try some other ones like this. I could have just used this and not compared it to the moon, to our moon. But I think compared it to our moon is easy. I don't know, it's just the same thing, whatever you want to do. This is the radius of the orbit of the satellite. So that's going to be 6.7, 10 to the third, cubed, over, maybe I should have flipped this, right? So I end up with the period right away, but it doesn't matter. You can do the algebra. Equals big G, mass of the Earth, over 4 pi squared. Just make sure when you divide in here, you put this in parentheses, and I'm sure you can find the period. And let's see how much we have left here. Okay. Suppose a planet is 4 times as far from the sun as Mars is. What would the period of that planet compare to Mars period? Well, so this is the T for that planet over T of Mars, right? Square equals, now that's a ratio of 4 to 1. And you have to cube that. Now that's 64, it takes square root of 64, you should get an 8. So the period of this planet is 8 times the period of Mars. Suppose the planet is twice as far from the sun as Earth is. Find the period in years. So I can just say, well, T of this planet over T of Earth, which is a 1 square, equals, now this is, and I'll write the equation, but this is a ratio of 2 to 1. And I would cube that, and I would make this a 1, and I should get square root of 8. The asteroid Icarus orbits the sun with a period of 410 days. What is its mean distance from the sun? Now I can probably compare this to Earth because Earth also goes around the sun. Okay, so I can say, well, T for this asteroid over T for Earth, which is a 1. It's quick. I would not use this equation. That's going to take, I think, it's going to take a little bit too long. Equals the radius of the orbit of this asteroid over the radius of the orbit of the Earth, and then I would do a cube. All right. Now I make this a 1. You look at the data table, and you can find the radius of the orbit of the Earth around the sun, and you can solve for T. All right. Pluto is that many kilometers from the sun. Calculate Pluto's orbit period in Earth years. So now just be careful, going back to 74. When you do this, you're going to find this T in years, because this 1 is 1 year. And you will divide it by 365 to find it I'm sorry, you would multiply it by 365 to find it in days. Right. Pluto is that much from the sun. Calculate Pluto's orbital period in Earth years. So I think we just compare Pluto to Earth. So I'm going to do it right here. P square. This is the radius. Okay. P. This is the radius of the Earth. This is given. You can look up the radius of the Earth, the radius of the orbit of the Earth, and you can just divide. All right. Oh, even here I said to use redo 64 and 66. Okay. Maybe you can try 63 also. You know what? I'm going to do 64 and 66, and maybe you can try the other ones on your own. How about that? All right. What is the height h above the Earth's surface at which all geosynchronous satellites must be placed in orbit? Now, geosynchronous satellites have a period of 24 hours, which is 1 day. We know another object that goes around us, which is the moon. So I'm going to compare this satellite to our to our moon. So T of satellite over T of the moon square equals the radius of the orbit of the satellite over the radius of the orbit of the moon, and I'll cube that. Now keep in mind that when I do this, I'm going to find the distance from the satellite to the center of the Earth. I must subtract the radius of the Earth to find the height. But I'm not going to do it here, right? I'm not going to write this as r what do you call it, RE plus H. Just going to leave it like that and just subtract later. Now, T of the satellite is 1 day, okay? Because 24 hours. So for the moon, it's 27.3, and I will square the whole thing. Now, the distance from the moon to the earth is given. So that's 3.8 times 10 to the 8. And you can solve this equation now. Cube. So what I would do here if I were you is figure this out, square it, take the cube root, right? Multiply by this bottom, and then you will get RS. But that takes you all the way to the center. And if you're only looking for the height, you just subtract the radius of the earth. Now 65 can be done exactly the same way. Okay, so we're gonna try it. Find its orbital speed. So this is the shuttle, this is the moon. So at this time we're looking for T, right? And we have the radius of the orbit of the shuttle. We have the radius of the orbit of the moon. So this is going to be TS over 27.3. Now keep in mind that we're finding this in days because this is a lunar month, 27.3 days. Square equals, this is going to be 200 kilometers, which is 2 times 10 to the 5th, plus the radius of the earth. I have to get all the way to the center, over the what is it? Distance between the moon and the earth is 3.8 times 10 to the 8. I would cube that. Now again, you figure this out, you cube it, take the square root, multiply by 27.3, you get TS. Once you get TS, it's going to be in days because this 27.3 is in days. And then you can change it. All right. Now let's look at 66. I think it's 80 to 66. Now here's the problem with this one. I don't know anything else that goes around Venus. So I can't use the proportions. I can't do T over T squared equals R over R cubed. So I'm going to rely on this, see if this one can help me. All right, so since it's asking for period, I'm going to flip this around. This way I end up with my unknown on top. So I'm going to say T of this satellite square, okay, over the radius of the orbit of this satellite cubed equals G. Now M is the mass of what this satellite is going around, which is Venus, over 4 pi squared. And we have to make sure you put this in parentheses. All right? So now the mass of Venus, you can look it up. The G is given. This is given. This here is 300,000 plus the radius of Venus, which you can find, right? And you can cube that, and then you can do the algebra there, and it shouldn't be too bad. Okay? And I think you can try the ones that I didn't try. I think there was only one that's left. Maybe you can give it a try with the third law. All right? And I know this is a long video, but that pretty much covers the law of universal gravity.
All right, I'm out. Peace.